Hello, everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. Um, you know, I was just kind of ranting about how awful DOS keyboard is at the beginning of the stream, so I'm kind of a little bit worked up now. So we need to kind of mentally focus, regain our focus, pretend that we're typing on a good keyboard, and just kind of rezone into a happy place in order to do an episode of Handmade Hero. Let this be a lesson to everyone out there. Picking a good keyboard company is very important. And I am certainly taking suggestions at this point. That said, we are in the middle of doing some optimization work on Handmade Hero. We yesterday finished doing most of the work of converting all the math operations to SIMD in our texturing routine. And we have a little bit more work to do on that, but we're getting kind of close to the end, and it's sort of time to start looking at how many ops we have and how fast we think we can make it go and other things like this. So I'd like to get right into that, but before I do, if you'd like to follow along and you have a working keyboard where you live, you can go ahead and unpack day 118 source code, because that's what we're going to be working with here on day 119. Now, let's go ahead and open up the editor. So, if you remember where we were at yesterday, we had just completed in our sort of hopefully quickly routine, which I think at this point we could actually say quickly. I think we could drop the hopefully at this point because honestly, I feel like we have gotten it to go rather quickly. Now, it's probably not as quickly as it could go, but we definitely accomplished our goal of making it go quickly. But at this point, we really just don't know how quick it is compared to what it could be, and that's sort of what we're going to be talking about today. So I'm going to drop the hopefully and say that we just have a routine that draws rectangles quickly, and we're going to move on from there. So there we go. Here is our routine working in all of its glory. And as you can see, it is quite a bit faster than when we started. When we started, it was taking somewhere in the neighborhood, I don't even know what it was, 280 cycles, something like this. Well, you know what? We don't really have to guess because we could, if we wanted to, switch to draw rectangle slowly and see. So if we actually go in here to render bitmap and switch it this way, right? Let's see here. P is undeclared. PX, PY. Oh, right. Sorry. This is supposed to be draw rectangle slowly here. There we go. And if I remember correctly, draw rectangle slowly has some extra stuff that it needs to take. We pass it the X and Y axis, the color, and then we also pass it sort of the texture, the normal map, and then the 3 bitmaps there. So I think that is everything that needs to get passed. So if we wanted to, we could sort of call draw rectangle slowly here, if that makes sense. Let's go ahead and do that. And we would need some timing on draw rectangle slowly as well, which I don't know that we actually have. It looks like we do have. So you can kind of see draw rectangle slowly running here. We can take a look at the time. We don't actually have this one doing any sort of counting on it, so we can't see what the cycles per pixel is. So what we should probably do is go ahead and get that the pixel fill call and put that in so we can actually see how many cycles per pixel it is, and then we could actually do a comparison. So draw rectangle quickly. Let's see what we got here. We have begin time block process pixel. So I want to do that in draw rectangle slowly as well. So that's going to be right here. And then we're going to do the same thing that we did here where we end time block counted. And we go ahead and count how many pixels we're actually trying to fill. And there we go. So let's see if that gives us a count. There we go. So calling draw rectangle slowly, as you can see, is 353 cycles per pixel there. And when we switch it, we are actually going quite a bit faster than we were going before. I guess it's like 7 times slower, or roughly something like this. something like that. So anyway, point being, we have done a pretty good job of getting it down to something that is nice and fast and usable, but we don't actually know at this point, and this is the thing I mentioned way back when we started a week ago, we don't actually know how long it should take us to fill any of this stuff. So we know that we're running a lot faster than when we started. We know that we're down in the 50s and we were in the 350s, and so that's all great. But what we don't know is how long should it be taking us to fill each individual pixel. We don't really have any estimate, so it's pretty hard for us to know whether we're done optimizing this routine or not. Now, we could just ignore that fact, and we could just say, well, we got it fast enough for our purposes at the moment. We don't really need to do anything else to it. And that's certainly a totally fine tack to take. If you just want to, have a crack at optimizing a routine, and then, if it pans out, it pans out. If it doesn't, it doesn't. You don't really want to be super precise about it. That's totally fine. But what I kind of wanted to show here is some stuff we could do to try to figure out roughly how long these things should be taking, or if we were, had maxed everything out completely perfectly, how long do we think these things should take? And then we can sort of have, an estimate as to, how close we are to good, if that makes sense. So let's suppose temporarily that we always had all the memory that we actually wanted was ready when we needed it, so we were not dealing with any sorts of memory latency or anything like that. And we're just going to talk about how many cycles do we think it would take for all of these guys to complete, right? So for everything in here that actually has to be executed, how long would it actually take us to execute them, right? And so what I want to do is I want to try and figure out a way that I can easily count the operations that we're actually going to do. Now, it's a little bit tricky, right? Because each one of these guys is, every single one of these guys has a different latency, right? Every single one of these guys has a different latency in the thing, and it's hard for me to look at the code and count them. So what I'd like to do is make some kind of, some kind of automated process, if you will, that will take a look at how many of these we're doing and give us some kind of an estimate as to what the total throughput for all of these operations should be, right? And again, this is best case, assuming everything was pipelined properly. And so what I'd like to do is go, all right, let's just take a look at all of these functions here. What if I were to just define all of these guys to do something else entirely from what they actually do, right? And so what I want to do is I want to go ahead and take this routine here, right? I want to go ahead and take this out, and I want to see about all of the functions, the _mm functions that we have. I'm going to pound define them to do something else, okay? So what I'm going to do is I'm going to go ahead and say, all right, let's take all of these guys. Let's do mm set ps, right? We'll do mm set 1 ps. And I guess it's worth noting that this stuff here, all right, you know what? Before I start that, I'm looking at this here and I'm noticing that we haven't actually finished SIMDizing it. We've still got some stuff here that's scalar. I doubt that this has very much to do with anything that we're doing, but let's just say this to do, Casey, remove this, because we can get rid of those. At the very least, you can see that pixel py is the same everywhere, so that's not really part of this loop, right? But pixel px is also a kind of a known value, so we could actually just be incrementing it every time instead of calling set, where it has to hoist this xi value out into the SIMD register. Does that make sense? In fact, I guess it's so simple we might as well just do it, right? If I set this guy here, pixel ps, if I set him to just be xmin, the place that we're starting, right? If I set him to be xmin, like so, then every time through this loop, I could, if I want to, just do an add ps, right? And add to him a value that steps by 4, right? because all of these guys, if I just add 4 to them every time, I get the next bank of 4 pixels, what the x coordinates are for the next bank of 4 pixels, right? So if I do pixel px equals pixel px plus the constant 4, and I just go ahead and do that at the end of the loop, right? That is sufficient for computing the new x values, right? So I don't actually know if that's better or not, like I said, but we can get rid, again, of some more of that scalar, right? More of that scalar operation that's happening there. So if I want to do that, I can just do this here. And we can probably remove those 4 x's now, because remember I said we don't really need the scalar versions of them anymore. And hey, it actually does look like that helped. You know, every little bit, it's weird, right? But if you take a look now, we're actually below 50 sometimes now. We're dipping into the 49 cycles. So yeah, making that wide was also, the compiler liked that as well. Now, one thing that's interesting here, I guess, also now that I see, now that I'm just looking at the stuff that we're doing here, we also have this pixel py, right, and origin y 4x. This stuff here really could have just been done once ahead of time, couldn't it have? I mean, why are we subtracting, you know, do we ever even use pixel py and pixel px other than in that one instance, right? And we don't, right? So these subtractions are constant. Yeah, I mean, this stuff is all actually not very good now that I look at it, right? We don't really need to be doing these where we're doing these. So for example, if you take a look at this, right? The subtraction to get dx is actually something that we could have just baked into pixel px to begin with, right? So we could have just said that this is pixel px here, right? And we could have just done this mm sub ps just at the beginning, right? We could have just done this right off the bat and said that's the value of pixel px. And furthermore, pixel py, well, pixel py doesn't change. Pixel py is constant across the row, right? So pixel py could be doing that just the same. So that was just us, you know, we hadn't really started looking at optimizing the code yet. So I guess, you know, again, we sort of get what we deserve there, which is fine. But anyway, so there we go. And hey, we're actually 2 cycles faster now, it looks like, roughly thereabouts. So that's good too. When I look at some of these other things here, you can sort of see, oddly enough, like, I don't even know, maybe the U and the V even want to be done that way, because if you look at what's happening with the U and the V, those are also going to be sort of baked in, right? We're doing this mul ps. This mul ps of pixel y here is never going to change across the row, right? So these two values here are not going to change across the row. And if you take a look at these two values, they're multiplying pixel px by whatever these two axes are. We could do that. We could actually have 2 variables that we incremented and sort of pull those out as well. But I don't really need to. I don't think we actually necessarily need to do that just yet. But what we can do is say, all right, let's actually just store maybe the result of these 2 multiplications up and then do the add in there. That seems pretty reasonable. It does create 2 variables we have to store, though. That one I'm less sure about. Well, let's try it. I don't know. I kind of got into it now, and since I'm into it, I just want to see. It's not necessarily the fairest test of them all, but let's just see. So we'll just call this like temp 0 and temp 1 just to test and see what happens. So if I were to do that, if I'm going to get this out of here, temp 0, right, like so, and get this out of here, so this is temp 1, and it's clear that those are constant across the row. Does that help the compiler at all? Does the compiler do anything smarter with that? And I don't know. It actually looks like that's a little bit worse. So it would rather generate those values from the mul. That's totally fair. So we'll leave that as it is for now. All right, so let me just do another, since that kind of happened, let me do a quick pass over this and see if there's anything else before we get down to actually looking at how long things take. Let's make sure that our loop actually isn't doing anything too incredibly stupid so that we aren't like wasting our time counting things that actually shouldn't never happen to begin with. So we're doing our clamping here of the U and the V, which all seems totally fair. We are doing our subs to get our fractional coordinates, and that all also seems fair. We then have to do our texture fetching, which at the moment obviously is having to be done in scalar, but there's not a lot that we can really do about that being in scalar because that is just kind of the nature of the beast. We don't have the ability to fetch wide, so that's just going to be that way. When we do our unpacking here, it doesn't look like there's anything weird that we're doing with the unpack. It looks pretty reasonable to me, right? It's just doing the standard stuff. We need to do, obviously, the and then we need to do the convert and so on. Let's see, we've got loading the destination, we've got converting to brightness. All of this stuff seemed pretty reasonable. So I don't think that we really had a lot of kind of pure stupidity in there like we did kind of at the top of the loop where it looks like we really hadn't played with anything. So yeah. Oh, and incidentally, for those of you who missed it on Twitter, Fabian wrote in and said why the mask move U SI128 was not helping. And he said it was because actually it is an instruction that should never be used for any reason, because I guess it is completely useless. It bypasses the cache. It's a non-temporal store, which means it writes past the cache. It does not actually write into the cache. So it's not just as simple as a mask move. It's a separate type of thing. We haven't really talked about that stuff yet, so I don't want to go into too much detail, but he basically said you never, ever, ever call this. Someone asked about it on the stream, and so I wanted to show it there, and we checked it out, and it was 3 times slower. And Fabian was saying, yeah, there's pretty much never a time when you can use that function, that instruction. He said it's basically always bad. So yeah, I guess that's just something to be aware of. So all right. We're down to 48 cycles per pixel, so that's a good thing. What we want to do now is we want to go ahead and start doing that counting, because I think we got rid of anything that was like obviously stupid in here. So what I want to do is I want to go through all of the actual MMs things that we call, and I want to just basically record the fact that we're calling them so that I don't have to count these things manually, right? So what I want to do here is basically say, okay, you know, every single one of these that we have, add ps, mul ps, let's see, cast ps, we've got and, or. Oh, well, we don't have an or there, I guess. Never mind. We've got comp GE. We've got comp LE. And let's see. So then we've got our load U, which is loading in that pixel value. We've got our min PS and max PS. Then we have our conversions. And we've got conversions in both directions. Should probably go ahead and do this. There we go. This will be much more efficient. So we've got EPI PS there. There we go. So that's all good. And I don't see anything in there. We have the extraction to do, but we're going to probably have to think about that a little bit, basically a little separately. So here's our and, here's our shift, and looks like all of that is covered. We've got our squaring instruction. We have a bunch of moles, which we've already counted. We've got our sub, which did we already do? No, we did not do the sub. Let's get the sub and the add in there. Here's our sub. We've got our moles, subs and moles. Convert PS EPI 32. We've already got one of those. And we got our shift left. Those we do not have yet, so those got to go in there. And there's our OR, finally. So there's our OR. There we go. And also an and not. So this looks like basically all the stuff we do. And I'm going to actually say that the load and the load in the store I'm not going to look at right now. But this looks like basically what we do for all intents and purposes. So what I would like to do is actually, this is very strange. I know this is a bizarre thing to be doing, but it is what we're going to do. I'm just going to define these guys to be something that counts for us, right? So I just want this to basically count how many of each thing there are, right? Pretty straightforward. So what I want to do is basically do something like, that. Count op. Like so. And this count op will, I guess probably what I want to do here is something like, I want to be able to print these out, right? Well, not really print them out. I want to be able to do something with them such that they can sort of be appended. So what I can probably do is actually, I guess I don't even really need to do a count op on them per se. What I could do instead is I could do something where we're just going to go like counts, plus plus, something like this, right? I think that should work fairly well, right? Okay, so we'll just do something that looks like this. And really, I suppose this is a good place for a macro. I can just do something that's like, okay, go ahead and search for that, go to the end, do a plus plus counts, paste it in there. I guess delete that off the end, and then that's the end of it, right? So now I've got something that's going to count all of those as they are actually being executed, right? And I'm going to need some way of actually making sure that these expressions all work, right? I need some way of these actually producing something. So I think I probably also need to wrap these guys in something, right? So I need to do sort of like a dummy, some kind of a dummy wrapper that will make sure, because in this expression, like a mul PS, it's going to come out, and it's going to need to be able to put something in there. Although, you know what? Now that I think about it, I suppose that's not actually true, because as long as these things are all just stuff that takes parameters, I suppose it would just kind of work in a weird way. I don't know if that's actually true. I'm not sure. I'm not sure if that's actually true, but I think it might be. So yeah, that's weird. I never thought of that before, but I guess if I just actually put these in here, we should actually be able to get the C compiler to just also do all the operations for us. Oops, that's just that. Yeah, that, and then just count the other ones. That's kind of strange. I never really thought about that before, but I think that actually might just work. We'll find out in a second, certainly. Yeah, all right. So that way it'll count. As you can see, I'm making the macro so that it'll basically count its own op, and then insert whatever was supposed to happen from the previous ops, which will be, which will be some kind of another count, right? All right. So here we go. And almost done. I guess shift by an immediate wouldn't need to count the immediate. So there we go. Yeah, I don't know if that actually works or not. It's pretty strange, but we're going to try it. We'll see how it goes. All right, so then I'm just going to I'm going to go ahead and make here a little struct for our counts. And again, I'm going to go ahead and macro that. I'm just going to go to the ++. I'm going to delete it off. I'm going to make an int here, search for that, and kill it. And then that way I can just kind of run through these and turn them all into something reasonable. There we go. And what we want to do for mm², right, is mm² is just a mul, right? So we want to increase the mul PS count when we do our mm². And that takes one of these. So now let's see if this ridiculous stunt actually works. When I say ridiculous stunt, I mean it. It's pretty ridiculous. So let's go ahead and make counts a thing that we can clear. Cannot convert from int. Oh, that's true. These guys, these M128s, that's okay. We'll just pretend that an M128 is an int for now. And that is probably going to be that. All right, initializing cannot convert from int to mm128i. That's also true. Gotta make sure that goes there. And then what's going on here? Our load u si128 cannot convert int star. So our load u, we have to at least define these to go away to nothing. Mm store u si128b. There we go. All right. Let's see how that goes. We still have a few problems. Syntax error on the semicolon. So load u si128. That's going to be int original dest equals op. We have to actually make it be something, though, I suppose. So there we go. Oh, we forgot squirt ps. And we forgot, looks like we did one other one improperly as well. So let's make sure that we've got everybody here. Define mm² ps a ++ counts mm² ps. And we got to add that to our guy here, squirt ps. And by the way, everything that I'm doing here is something the compiler should output for you. It's absolutely absurd that it doesn't, but that's just what you get when your development environment doesn't care about low-level programmers, right? I mean, this should just be a thing that you just get automatically from the compiler, and it's kind of ridiculous that you don't. So let's see here. Convert ps. I guess I didn't have this one. Convert ps. I did convert TPS, but I didn't do convert PS. So there we go, and that looks like the last one. So there we go. Everything looks good there. Our add PS binary equals. Oh, that's outside, so we need to do an undef of add PS here. Although that add PS actually does happen, so I guess technically we should really sort of be counting it. So we're going to be one add off because of this guy, if that makes sense. But let's go ahead and see here. Undef add PS. Okay, so now we do not need to be compiling in release mode. anymore, right? We can go ahead and do that. And we can take a look at how many things we actually asked for. Now, that's not the same as how many things happened, right? Because the compiler is going to do a bunch of stuff to it, but it's just a way for us to count all of the actual, excuse me, all of the actual instructions that we're actually asking the compiler to generate on our behalf. So when we get down to the end of this here, so we're going to go counts here, right? We're going to go ahead through here and down to here. I guess we will have to also get rid of our texture fetch loop because this is all going to be complete garbage data. So let's go ahead and do that. Okay. Just got to clear these out because otherwise the compiler will complain. And cannot convert to int. Oh, right. I didn't have to do that. Those were integers. So that's fine. I can just do this. All right. So if we do this count, I should in theory be able to run this and actually see what the counts all end up being, right? So if we take a look at it here, here we go. And you can see that we've got, I mean, assuming that I didn't mess something up, right? We've got how many of each of these things we're actually calling every time through the loop. Now, I want to actually check to see if this looks like it makes any sense. I don't want to just assume that that's actually correct. So let's go ahead and pick one of them. Let's do min ps and see if it actually looks like it's getting called the right number of times, right? So that's 1, 2, 3, 4, 5. That's just right. And then max ps similarly. 1, 2, 3, 4, 5. Yeah. So that all looks pretty good. square looks good. Add ps. So let's check one more of them. Let's do a big one now. mul ps. Well, that's 73. Let's do add ps. So add ps. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that should be 18, and it is. All right. So this basically tells us, right, what our total operation count is. Right? That's the whole thing right there. That's how many operations we actually needed to do. And we could, if we wanted to, also go ahead and start to actually look at these and multiply them by their actual latencies, right? Like, for example, I could go ahead and take that count struct down here when it gets to the end. I could produce another count struct that's actually the latency for these guys, right? So if I took this count struct and I just come down here and I say, all right, you know, right after we finish, we're in here, I want to take this count struct and I want to say latency counts, right? Something like this. I want to go in and do, well, I guess I don't even need to make a struct for it. I could just make these ints be floats. Int 32. There we go. And each of these can just be whatever the count was for this guy, right? Times whatever the throughput value is. So we can go over to the Intrinsics guide. And we can take a look at what these actually are, right? add ps, and so on. Now, of course, the throughput value differs sometimes, but thankfully for some of these, it's going to be the same. So the throughput on the add is 1, right? The throughput on the sub is probably the same, you would imagine, and it is. The throughput on the mul That's not what I want to do. Is 1 on this one. We are not a Haswell processor. The throughput on the cast PS is really difficult to estimate because I suppose the cast PS is not really latent unless it has the situation Fabian was alluding to. So I guess we don't actually know what that one is. We'll assume that we can do it for free somehow and not count it for now. All right, the throughput here, I guess, so I don't actually know what processor family we're running on right now. So what I might do is just take a quick second to figure out. Let's see. I want to be able to right-click on my computer and hit Properties. So this is a Xeon 5580, right? So what is a Xeon 5580? What is the family? Or the core type, I guess is what I want to know. Okay, it's launched. Thank you very much for that. Can you tell me the core type? I don't care about any of these things. Give me some more, give me something better. Nehalem. So that's what it is. So on a Nehalem, it's 0.33. That's kind of crazy. But that's what it says. Let's hope that's accurate. Right, and PS is actually says that that's what that is. So we'll trust him for now. We should probably be looking at Agner Fog because that's probably a more trustworthy source. But at the moment, that would take a lot longer. And time is of the essence on the stream. Comp GE PS. Again, it looks like we don't have a throughput on here. I believe the throughput on this is 1, but we should probably double check it. Anyone who wants to go ahead and double check that on Agner, that would be good. Comp LE. I think that's also 1. Comp LE. Yeah. And then we've got min and max. So min PS and max PS, both 1. And then we've got convert TPS EPI32 and convert. So what are those? Convert PS EPI32. That is 1. And this one is also 1. A lot of these guys are just 1. And if you're wondering why I'm putting in multiply by 1, just mental note. So it's like, okay, we got it. Convert EPI 32 PS. That's going the other direction. Also 1. Then we've got our AND. Presumably this is the same speed. It is. Looks like the bitwise ops are all 1/3 of a cycle. Presumably, I'm just going to go ahead and guess that the AND not is the same. There we go. You know what? I should probably do 1.0f over 3.0f and do like 1/3 or something like this. And have these guys actually just use that so that it's a little more precise than the ridiculous version that they were using on the forum there. All right, so there's the and not. So let's take a look at the shift right, SRLRI EPI 32. That's a throughput 1 as well. And so presumably the left shift will also be that way. So SLLI EPI 32. Yep. And the squirt. Now squirt, if I remember correctly, was a pretty brutal one. So on the Halum, that's a 16 cycle. All right. So we now have all of these guys put together here, right? So I am going to go ahead and do a little more ridiculousness. I'm just going to put all these guys inside a sum, like so. These guys are, I guess, just 0. We'll go ahead and use our power of macro again. So search for that. Actually, I guess I should do it this way. Search for that. Okay. And to continue the absurdity, we'll just do sum of A equals A, and then total plus equals A, right? So yeah, that way we can do a total equals 0, and then at the end we'll get an actual total, right? Seems reasonable. What is the problem here? Initializing from int to real 32. Oh, well, you know what? That's pretty easy for us to fix. We can just go ahead and change all of the stars. Man, today is some good hackery. This is just some good hackery. If we just change all the stars to commas, right? Then we can do like latency and the thing, right? So then we can just do real 32A latency times that thing, like so. And we can make that be what we add to the total as well. Totally crazy. Don't try this at home. So yeah, there we go. And in theory, I can now go get some sort of a throughput total for myself. And this is only in theory. So where are we at? Here's our counts. And here is our total. Well, isn't that fancy, ladies and gentlemen? Isn't that fancy? How does that number look to you? 218 total cycles of throughput. That is if we were to do everything exactly perfectly so that all the instructions just slammed to the processor, that's what we would get. Well, we are filling 4 pixels at a time. That means somehow, right, our actual measured throughput is slightly lower than what the theoretical maximum would be if all of those things were just issued back to back. Okay, so that's a good sign for starters. And I assume that just means that a lot of these things are getting issued in parallel. That's basically the only thing I can assume. In order for us to be that low, what that essentially means is that we're issuing multiple instructions per cycle so that we're not actually ever having to even weight the throughput total. We're sort of overlapping things as we go. So in order to calculate a total for this, the next lowest total that we could get to, this is, so just to say, I was kind of hoping we would be above this total already, but we're not. So this total is basically what the total would be if there was only one unit executing all of the instructions, but they were all perfectly overlapped. So you just streamed them serially through the processor, maximum throughput. Now what we saw is we actually got that, right? We're actually getting slightly below that. It says that would give us about 54 cycles total, 55 cycles. We're actually getting like 48 cycles right now. So we're actually better than what that suggests, right? And I think we didn't count this add, right? So this add, it should actually be a little bit higher. So what that means is we're actually getting a lot of pairing in here. And in order to count the pairing, we would need to know essentially how many of these instructions we could issue at any given time, right? Now, I have no idea how many units this guy has. I don't even know where I can get that data. So this ought to be interesting. Let's go ahead and look at the W5580 again. I don't know where to find out how many units the thing has. I don't think they tell you on here. In fact, I'm pretty sure they don't tell you. But we do know it's a Nehalem core. So maybe we can take a wild leap and see. Okay. So let's see. What does it have? Okay, we don't care about caches right now. We don't care about any of these things right now. We just want to know what kind of units it has in it. And this does not tell us that. So maybe I can search. Wow. Look at this stuff. Price for 1K unit? Those are expensive. All right, anyway. So I wonder if I can say like ALUs or something. Just, I don't know if there's something in here that would tell us how many ports it has, how many things it can issue at once. Because that's really all we want to know. Let's see, technology, scaling up issues, rapid execution engine, blah, blah, blah. I don't know if this actually helps. This may be one of those things where we just have to put it on hold for a minute and actually ask someone who knows better than we do, which would be nice to have here, but unfortunately we don't. Let's see. Yeah, no, this is not what we want. I just want to know how many instructions it can issue at a time. Well, let's take a look. Nehalem. How many ALUs? Texas A&M. Okay. Let's see here. Cache hierarchy, main memory, virtual memory, Nehalem data pipeline, out of order execution, execution pipelines, load and store, SIMD operations. Well, this might have some of that for us, but I don't know. Let's see. What registers the Nehalem core? Contains the circuitry to carry out 2 double precision or 4 single precision positioning in each of the 2 FP units accessible through ports 0 and 1. Okay. So we have 2 FP units that we can issue to. So on any given cycle, that would assuming that I'm reading this correctly, that would mean that we could issue, for example, 2 multiplies or adds or things like that, assuming that they're the same. Steady state indications. Each core can retire 4 double precision or 8 single precision floating point operations each cycle. So that, yeah, that would make sense. The non-modular throughput in core quad core cycles. So that is reasonable. Let's see if there's anything else that we can learn from this here. So assuming that there were 2 of those, and if we look at the kinds of stuff we have here and separate these out, right? So these are all the guys that go through. We don't, let's see if we can get, does this actually have the port listing on it? So unfortunately, what we don't get from this piece of information here, right? From this Intrinsics guide, it doesn't tell us what instructions can be issued with what other instructions. If you remember back to when we talked about CPU architectures and optimization, I was saying that, I believe an x64 processor can issue up to 4 instructions at once, right? But, which instructions they are matters. It can't just issue any 4 instructions at once because, as we talked about, again, that same time when I was talking about this, I was saying there has to be a unit free that can actually accept that instruction. So if there was only 2 multipliers total on the chip, right, that it doesn't matter if it can, in theory, issue 4 instructions. It can only issue 2 multiply instructions because there's only 2 possible places to shove those multiplies. There aren't another 2 units to kick off, even though the front end of the processor would be totally capable of doing so if those units did exist, but they don't, right? So what we want to see here, if we were going to try and get this calculation down to something more accurate, what we want to see is we'd want to know which of these instructions, how many of them we can issue per cycle, basically, right? And so that would give us an idea of what these multipliers would actually be. Now, if everything could be issued 2 per cycle, if 2 per cycle was just the average that we could issue, let's say, then we would know that we just take the total and we divide it by 2, right? So we'd take that total, and instead of dividing by 4, we'd actually divide it by 8, and that would give us 27 cycles would be sort of the maximum throughput that we could ever hope to possibly achieve using this set of things that we're doing, right? So, I don't know, right? I think we're at a little bit of an impasse here. We're going to need more information about the particular process that we're on in order to get a better estimate. But I'm actually relatively happy, even though I don't think we can do that without a little bit more information and something that I probably don't want to do on stream. Like, we could go hunt through Ogner fog tables. The ports are probably listed on there. We've actually gotten a piece of information that's actually pretty valuable, which is that even just right now, knowing that we're at about 48 cycles or something like that per pixel, we're actually very, very close to the threshold where optimizing it further just in terms of the actual mathematical operations, if we were going to keep doing them, wouldn't actually get us very much faster, right? Because if it really is true that there's only like 2 multipliers or two floating point things can be issued every cycle, looking down here at 27 cycles is like, okay, we're not running very far behind the actual theoretical throughput, right? Now, could we get a little closer? Probably yes, but it's kind of a point of diminishing returns there, right? It's like we don't have that much headroom to go. So it sort of looks like I actually got what I wanted from this, even though it's not particularly accurate yet, which is I have an idea now of whether or not something like, say, memory latency was hurting us. And it looks like it really wasn't, right? Because look at how, with how close it appears that we are there, it looks like the cache was operating quite well for us, very friendly. It doesn't look like we're having a lot of problems with stalls or anything like this, right? So that's a pretty interesting thing. That's a pretty good thing for us to know. Now, what I'd like to do as well is take a quick look at what happens under a couple of different conditions here. So what I want to do is make some way that we can if-det this out easily. So I want to basically make a thing that's like define count cycles or something like this, right? And what I'm going to do is I'm going to do an if on that, right? So that if that is not defined, right, then it lets things operate properly, right? So we do an if count cycles, and then down here we do an if count cycles again, right? Like so, if count cycles. And that way we can just turn it on and off anytime we want a cycle count, and it doesn't actually do anything weird for us, right? So here we go. Got to change this around though. Okay. So let's take a look at something here. Oh, right, we're in debug mode still. Debug mode is quite a bit slower. Okay. All right. So here we are at our 48-ish cycles per pixel. What I wanted to do is take a look at how bad Juan screwed us here. Let's just get it out in the open. Let's look at how badly Juan Shun screwed us. That's where we're at. He is the person who demanded that we put in gamma correction. Honestly, I don't think it made very much of a difference, but he's correct. It was a good thing to talk about either way. It was important that we looked at it, even if we choose to get rid of it. And basically, having the squirt in here is really bad. Okay? So what I'd like to do is see what happens if we get rid of the squirt. What will our performance look like then? So we've got two cases where this gets used. We have a mul PS here. so we're doing our square. So what I'm going to do is I'm going to come down here, and instead of square ps, what I'm going to do is I'm just going to remove that, right? So I'm going to say, all right, I want to define square. We're going to undef that, square. I want to define square a as just a. So square does not do anything. And then I'm going to define squirt ps to also not do anything. So I'm just undoing the gamma correction so that it's just gone, right? It's gone. And so if I run that, let's see where we're at. Oh, well, that doesn't look right, though. So we've got some kind of weird fringing going on. So what did I do there? That should work, should it not? To do the squaring. I wonder, do we have something gamma corrected that I'm not thinking of here? Let's see here. Square, we've got the mul ps, but so that's just going to leave things the same after doing the inverse. So that's all should be fine. Let's see what happens here. The desk gets raised to that power, so that's fine. And then we do the square root after we're done to put things back. So why are we getting that? That's a little troubling to me. What's going on there? Because that should not be the case, right? That is not what we wanted to see. Something is amiss. Something is awry. And I'm not sure what it is. So it's like the clamping isn't actually working. Where is our clamping? So we do our sub PS here. Texel. Mul PS dest r, and those are squares as well. Yeah, I don't know what the problem is. Does anyone see what the problem is there? I've only got 3 minutes left, but I'd like to know what's going on there. Right, you can very clearly see that around the edges, right, we've got that problem. Oh, I know what we probably have to do. Ah, yes. When we load the bitmap, I always forget exactly where we are with things. When we load the bitmap, we actually converted the bitmap. We converted the bitmap that way as well. So what we would need to do here is we would need to not do this in and out, right? That's all we would need to do, I believe. Oops. That was not right. sRGB to linear 1, linear 1 to sRGB. I take that back. We would need to move this below. That's what we actually need to do. Of course, that does not look good at all. But that's what should be, right? Because if we pre-multiply the alpha, that's what actually should be working, right? Because we can't leave it with the conversion. Leaving it with the conversion like that means that the alpha won't be the correct value for compositing with pre-multiplied alpha, right? Because it's doing the pre-multiplied alpha as if we were going to do an sRGB conversion. So, but we should be able to just leave it without doing the pre-multiplication and then pre-multiply after, right? And for some reason, that gives us completely garbage values, oh, duh, because Texel A gets converted. Yeah. Try that one more time. Oh, See, everything's going to be 255 there. Oh, wait, no. But that's fine. That's still fine. I just didn't use the variable I actually set up. Slow day on the stream. All right, so that's fine. So we don't actually need to do any of that. I just wanted to verify that we didn't have some other bug. Obviously, we don't care. I'm just doing a speed test, so that's all fine. So that's all good. Nothing to worry about there. So doing this speed test, it looks like Juan has not hurt us too badly, right? You know, it's not great. You know, we've got like 6 cycles or something that we saved from not doing the gamma correction, but it's not awful, right? It's not like it's twice as fast or something like that. So at the moment, without doing any more work to optimize this, Juan could rest easy knowing that he has not ruined all of Handmade Hero with his gamma correction, right? So okay. So at this point, I am fairly satisfied to say that this is a pretty reasonably optimized pixel loop, all things considered, especially when you consider the fact that we've got this ridiculousness happening in here that has to go fetch all these pixel values, which is kind of ridiculous, right? So it looks pretty good to me, actually. It's not that slow. Could it get faster? Yes. Could it get more than twice as fast? Probably not. And so I think it may be a good time, after having done that count, I'm pretty happy with where that is. I think it may be time to move out one level and start to look at how to optimize the things that are around this pixel loop. Because I think the pixel loop itself is actually not so bad. So that's probably what we'll start doing tomorrow. And at the moment, we will go do some Q&A. So we can answer any questions that people might have. Stellar7 asks, is this what you were looking for? Oh, yeah, this is what I was looking for. That's pretty cool. So there's load and store units. We don't care about those right now. We've got integer mmx ALU branch integer MSA with an FP add, FP mul, SSE mul, integer mmx ALU. Oh. Wait, but this looks weird, doesn't it? Looking at this diagram, I should probably try to bring this diagram up on the main screen because it's a little confusing, honestly, Stellar7. So let's see here. That is Wikimedia Nehalem diagram. Let's see if we can get that up on the screen. It's this guy. Oops, not that guy. This guy. So it's a little confusing looking at this because if you look at this, I'm just looking at where the multiplier unit seems to be, and like it looks like it's single ported, doesn't it? Yeah. So I mean, they said that it could do that. It had 2 units capable of doing a floating point multiply, but this diagram would make it look like there's only 1, wouldn't you say? Because here's FP mul. It's on port 0. I don't see any other FP muls. There's an FP add, right? But I don't see another mul. So I could be misinterpreting what this diagram's trying to say, but that's a little odd. That's a little odd. If you could only issue 1 multiply per cycle, then that would mean that we are basically at our, I mean, we're like right at the limit of what we could possibly do if we have to do this many multiplies, right? Because if I turn on count cycles again, most of what we were doing was multiplies, right? And so if we take a look in here, let's go ahead and stop in here. So if we take a look in here, right, we had to do 73 multiplies. So if you could only issue one multiply, if you could only issue one multiply per cycle, that means that essentially we know that even if everything else was perfectly pipelined with it, we would take 73 cycles just to do the multiplies, right? Because they can only be issued once every clock at a maximum, right? So assuming that we did that, let's see what that value comes out to be. So that means just the multiplies would take 18 cycles by themselves. So that's kind of crazy, right? But yeah, 18 cycles per pixel. Would it be worth timing just the load stores with no ALU ops present to see how much is just memory bound? Yes, but you're getting a little ahead of us there, Grumpy Giant. We haven't actually aligned our loads and stores yet, and we haven't actually talked much about the loads and stores at all. And so what I kind of wanted to do was do that in a separate pass. So tomorrow when we kind of step out one level, we'll time it, and we'll time it without the ops, and we'll see how it goes. But if you want to try it right now, we could jump the gun since you brought it up. I'm totally happy to just type it in. So let's see here. We have an O2. We turn off the count cycles. So here we are, and we're running at 48-ish, right? If we wanted to turn off all of the fancy operations that we're actually doing, right? And we just instead did some loads and stores here. Unfortunately, it's a little tricky because in order to know where we're fetching from, we have to at least do this many. But we can go ahead and get rid of most of this stuff, right? So once we have all of our samples, trying to think of, we have to have a way of doing this so that the compiler won't optimize these guys out, right? We have to have it so that they won't optimize out. So what I could do is do an if 0 here, I suppose, and we just go through, and before we write, we just do something like this, I guess. MM128i out equals MM or SI128, sample A, sample B. So basically I'm just, compositing all of the samples together into some garbage pattern just to make sure the compiler has to actually load them, if that makes sense. And then it'll go ahead and do that right. Another fantastic wild pattern here. So looking at that, that's 16 cycles, looks like, right? And I don't know if I can trim it down any more to be any closer to just memory ops, because we have to know where to fetch from in order to if we don't fetch from the actual locations, then it would change the cache behavior and it wouldn't necessarily be the right kind of test at that point. So I don't know that I can actually get rid of very much more. The compiler will get rid of FX for us, presumably, because it is never used. But it looks like that's like the minimum, right? So 16 cycles, just to put that into some perspective there, it's got to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. I mean, I guess what I would say about that is it's possible that we're stalling on the memory here a bit because 16 cycles is probably a little bit high. What we could do is we could try blasting out as another test, right? We could try blasting out without reading in these guys, right? So, what we could do is say this stuff, we're actually going to if zero around the whole thing, right? And what we'll do is we'll take sample A, B, C, and D, and we'll actually just derive those from values we already had, right? So what we'll do is we'll say, we'll make this be an cast PS, right, of, the X value or something like this, right? The fetch X, right? Oops. I guess that doesn't need to be a cast. That can just be fetch X. So we can just do something like this. In fact, I could just do it this way. Out is fetch X. And then or fetch X, fetch Y. Oh, it's not fetch. It's fetch X for X, of course. For X. For X. And there we go. So that'll just write out complete nonsense. And so, yeah, so you can see that is 3 cycles per pixel, which is quite a bit better. So a lot of that time there was spent, I guess, doing sort of, well, we don't really know. We know that we had to compute fetch X. So, I mean, technically, right, we don't know how much of the time was just spent getting the crap out of the the MM128 register, right? So we don't really know it was waiting on the textures. We don't really know that it was the fetch. It could have been other stuff, technically. But it does seem like maybe this is a fair chunk of the time, right? Which is what we would have expected. Is fetching those texels is very expensive, right? You counted MM and PS wrong. I'm surprised I didn't count more than just MM and PS, but let's go ahead and take a look. MM and PS. So it looks like it's getting counted properly there, right? Pound define MM and PS counts, right? That looks correct to me. So let's take a look at the bottom one. Ah, there we go. Okay. Thank you for catching that. Are you doing pre-multiplied alpha? Yes. Out of interest, could you run the game with Task Manager open? I'm interested to see what the RAM CPU are doing. Well, the RAM isn't doing anything because we just allocated all the memory in the machine when we started up and then never actually touch it after that, right? And the CPU won't do anything either. The CPU will be like hardly anything. Who is? Oh, right, OBS. I'm like, what's taking all the time? Oh, right, the thing that's streaming. Of course, makes perfect sense. So yeah, Task Manager, we're hardly using any of the CPU right now, right? I don't think, anyway. So there you go. Is this what you wanted to see? And like I was saying, we're not, we're on a this machine, old as it may be, is a beast in terms of core count. So you can see how many cores we've got here. We're only using one. And these are not actual cores, they're logical cores. So it's probably, I don't know, this machine probably has, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is probably a dual proc, each of which has 4 cores, would be my guess. And then each one of those cores has 2 hyperthreads. That's my assumption. So eventually, and hopefully not too long from now, we will actually use all of these cores, and we'll get quite a bit of speed up. But right now, we're not even close to maxing out the performance of the CPU right now. Not even close. All we did was look at 1 core throughput on our pixel fill routine. Right? That's all we've done so far in terms of optimization. We're not even close to using all the power of the CPU. Will this game only work for your specific processor? No, this game will work on any SSE2 capable processor, which is basically any PC processor on a Mac or on a Windows machine. Are you going to update these textures EX the yellow background? Well, the yellow background is actually there because we turned off ground chunk updating, right? Because we haven't gone and redone it with the new rendering system. And we had a bunch of stuff we needed to do with that anyway, right? So if we turned it on, we could see the ground tiles, right? They're in there. But we aren't working on that right now, so that's why they're not there, right? The texture fetch should be L1 cache fetch. Well, we don't know that, right? You know, we would hope that that's true. In certain circumstances, but we don't really know if that's always true, because it could be that the processor can't see it in time or other sorts of things like this, so we don't really know. And so I feel like it's too early to say something like that. In an alternate universe where everyone likes games but no one cares for art, so game developers don't need or use art assets, do you think those developers would spend as much time carefully optimizing things? I don't know what that means. Probably yes, because the reason you optimize stuff is usually so you can do more things, not so that you can use art assets. Like if you want to have 100,000 guys in a battle, it don't matter if they're all red rectangles or bitmaps of the guy, right? Or in 3D, it doesn't matter if they're little artist mannequins or fully modeled dudes. Now, maybe you could argue that if you're doing art that's going to look bad anyway, then it can be lower polygon count, less textures, all that sort of stuff, which does help you. And yeah, that's true. But you'd still have other things to optimize, right? It's not just being able to... Art assets aren't the only thing that require you to do optimization. Any ideas why one of my cores get maxed out running Handmade Hero with the XCB platform layer? Yeah, that's what should happen, basically. One core is getting maxed out when you run Handmade Hero. because we are running basically full speed right now. Well, that's probably not entirely true. Now we're probably running faster than 30 frames a second, but that's a separate issue. But one core should at least be pretty heavy usage. But Windows is free to move that around, so it's not necessarily the case that it will show up on exactly one processor graph. So what you'll typically see when you run Handmade Heroes, you should see basically a fractional percentage usage of the total CPU power, which is 1 over the number of cores in your machine, right? 1 over the number of hyper cores, basically. How did taking out the gamma correction, 3 square roots with a throughput of 16 cycles and 3 multiplies, only speed the loop up by 6 cycles? Well, the answer is that these things are overlapped, right? Once the processor kicks off a square root, it's free to do other stuff, right? It's not sitting around waiting for that square root to come back. So the fact that we're getting rid of these things that are worth 16 cycles, well, it's 16 cycles end to end, but inside that 16 cycles, the processor can grab all sorts of other work to do, right? And especially with these sort of out-of-work processors, even if the compiler did a lousy job of scheduling the instructions, the processor is still grabbing all sorts of future work to do while we're sitting around waiting for those square roots to finish. So that is the key. That's the thing we talked about way back when I talked about pipeline processors. If you don't remember that, go back to the original episode a week ago. I think it was last Monday or whenever it was, last Monday or Tuesday, where I talked about how pipelining works. Basically, processors have, every cycle, they've got a lot of things in flight. They issue new instructions, they pick up old instructions that got completed, and there's this pipeline of stuff that's moving through. So getting rid of something that takes 16 cycles, these things are not put end to end. So it's not like you saved 16 cycles. All you did is get rid of one 16 cycle thing that had to get overlapped in there somewhere. And so usually what you end up talking about is more about when units are free to execute stuff and how many total units you had and how busy they all were, right? And so that's why I was trying to get a little bit more information about that, but we don't quite have what we need to really compute it all out. But if you were to use more cores for drawing, how would you split up the work? Well, we're actually going to do this. That's what we're going to do next. So stay tuned. Next week will probably be all about splitting up the cores for drawing. What's the floating head? It's our little familiar. I didn't see the definition of mm², but if it's a macro, you're calling it with an intrinsic. So either A, compiler isn't eliminating common sub-expression and you're losing perf, or B, it is doing common sub-expression elimination and you're miscounting instructions. I believe neither of those two things is true. It is doing common sub-expression elimination because we checked that the other day because someone asked about that, and it did actually correctly do it. But I'm pretty sure that we don't, because you can see when we did the count, we just counted it as one multiply, right? So I'm pretty sure the answer is actually C, none of the above. But I don't know if that answered the question. What's that drum-like background noise? Yeah, the drum-like background noise is Amazon.com. They've been building buildings next to our apartment for a very, 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 very long time. Do you see all the questions and select from them, or should I write again if you miss my question? Yes, I do read all the questions and select from them, but I only answer questions that are on the topic that we're working on, generally. I answer off-topic questions before the stream starts. So if you have a question that's not about programming this thing that we're programming right now, then it's usually you have to come during the pre-stream if you want me to answer it. In case your processor supports constant rate TSC, could this significantly distort the reported cycle count in a way that matters, or is such possible inaccuracy insignificant for what we are doing here? No, it can't. So the answer there is it very much depends on the operating system and the processor, whether or not things like this are important, right? This particular machine, I believe, is not in a state that will ever be a problem. But it's entirely possible to have, I remember this happening to me in the past, it's entirely possible to have a processor, especially if it's on a laptop, that likes to vary its cycle rate right in the middle of when you're trying to time things, and it creates a lot of problems. So I have seen stuff like that happen before. It can happen. What you want to try and do as much as possible is put your machine into its like no power saving state, and all this sorts of stuff. But fortunately, I believe on most modern processors now, if your machine is relatively new, they don't have that problem anymore. I think they actually try to report back stable RDTSCs to you. I could be wrong about that, though. How does the CPU do things ahead of time if the code is supposed to be executed in order? Well, it just looks to see whether there's something further along in the instruction stream that doesn't depend on anything that's still being done. Because technically, when you write code, it doesn't have to be done in order. It just has to be done in order for any things that depend on each other. So as an example, as a really simple example, right, take a look at all these guys. None of these textile values depend on any of the other textile values, right? So if it issued this textile value and did these instructions, right, if it was issuing these instructions, it could easily go grab some of these other instructions and execute them without having to wait for it to come back. So for example, it's got a square that's going to be a mul. It's a mul followed by a mul, right? So it can't issue the second multiply until the first multiply is done because it uses the results from it, right? But if it wanted to, it could just go grab another multiply that was totally unrelated, like this one or this one, right? These are multiplies that don't have anything to do with each other. So that's how the processor picks them out. It just goes and grabs stuff from further down that's like, these things don't depend on each other. So the things that control how many things you can issue are those two things. Well, they're really three things, right? They're how many instructions per cycle can the processor just decode at all? Which again, I think on x64 is like 4, but I'm not sure. It might vary per processor. So it's how many can it decode? Then there's how many of them that it decoded, those go into like a window, right? And you're going to actually be executing from there. So in that window, how many things are independent, right? How many things could it actually pick from? And of those things it can pick from, how many units are available to do them, right? So there's a ton of things in that state, right? There's a ton of things that determine how many of the total number of instructions that a processor could actually push through the pipeline, will it actually push through the pipeline? And those are exactly the kind of things that, again, if you study this stuff, if you're a serious optimizer, I am not. Like, I am not an optimization guy. But if you're an optimization guy, that's the kind of thing you tend to know for the processors you work on, especially if you work on like a console or you're targeting a very specific processor, right? You're going to know that. And that's the kind of thing that, like, for example, Intel people can help you with if you're working on a game, and they have DevRel guys. You can be like, can you run this on the sim or something and tell me why it's not getting the net right? And so, I'm just showing very basic optimization techniques on the stream here because I'm not a hardcore optimization guy and I can't tell you how to do, super crazy optimization. Not on this processor anyway. I could probably do that on the 360 because I knew that thing really well. But I couldn't tell you how to do that here. And so, I've just given you the basics. Do you expect a 16x speedup from multi-threading? Probably not a 16x speedup, no. We haven't actually done any calculations to know roughly what the speedup would be, so I'm not sure. But it's pretty rare that you get a perfect n-way speed up. How do you select the instruction set for optimizing? So we showed this on a previous stream. Basically, the answer is it's not an exact science. And I just use the Steam hardware survey. It's not perfect by any means, but it's what we've got, and they're nice enough to make it available, and it's better than not having anything. So there you go. So if you take a look on here, right, you can kind of drop down this other settings thing, and you can see, by looking at this here, assuming that these stats were gathered correctly, sometimes they break. There's, caveat, caveat, caveat. But you can look at this and kind of go, all right, am I going to target SSE 4A? Well, only if my game is targeted at the highest of high-end gamers, right? Because a full 3/4 of the people, almost 4/5 of the people on Steam, don't have it, right? So I'm just limiting my potential market there by a fair bit, right? Similarly, am I going to target SSE 2? Well, okay, nobody on Steam this month, apparently, who played actually didn't have SSE 2. So that's what we're using. It seems like kind of a no-brainer. You're probably, if it's a person who's going to ever buy this game, they're going to have SSE 2. Because, pretty much any gamer who's even ever going to hear about Handmade Hero will have played a game on Steam at some point, probably, right? And so you're pretty much safe on SSE 2. SSE 3 looks pretty good, right? I mean, that's a very fractional amount. So if you wanted to target SSE 3, it looks like you totally could. And even SSE 4 might be something you could think about. 4.1 and 4.2 are pretty well covered. It's really just that A that's new enough that it's not on there. So that's one way to do it. I'm going for the 99% case, basically, right? I'm saying SSE 2. If we wanted to use SSE 3, I'd be fine with that. I'd rather not cut out a fifth of the market, but, if there was something that we really wanted to use in SSE 4, maybe we'd use it. I don't know. But that was fine. And again, the software renderer is something that we're kind of just doing as an optimization case. So, in the software renderer, if we wanted to use something in SSE 4A, that'd be fine. It's really more when we're doing any SIMD in the main line of the game that will be running on all the end user's machines. We don't really want that to be using something that the end user probably doesn't have. Isn't the Unity survey results pretty different from Steam hardware survey results? I don't actually know anything about the Unity hardware survey. I've never looked at it before, but I guess we can take a look at it now. I suppose that's standalone stats, probably. CPU, it doesn't say. Let's see if it's in here. CPU models. Well, I mean, I guess we could try to figure it out, but they don't seem to actually tell us, unfortunately, unless it's somewhere else. Doesn't look like they say about the SSE capabilities. I don't know. Yeah, if they have that, then sure, it'd be cool to check it out. But I don't know. You'd have to send me a link. What are the gains you get from writing your own software renderer as opposed to using something like SDL that does hardware software rendering? Okay, just to be clear, I'm assuming that's coming from somebody who doesn't watch the stream much. You do not want to write your own software renderer. We are not writing the software renderer because we want to do something. We're writing the software renderer because we wanted to show the entire code that gets executed to run a game. So what we've actually done is we wrote essentially what the GPU does, but we wrote it on the CPU so that I could show like how it works, right? And so that's why we're doing the software rendering, is so that we could have the whole code, everything, right, and see how it worked. We will actually be calling the hardware, we won't be using SDL because we don't need it for anything, but we will be calling OpenGL or something, possibly Vulkan if it's out in time. We will be calling the hardware to do the final rendering for the game. Can a processor work through different calculations, add, multiply a square root in each cycle, or do they each need their own cycle? So basically, that's something, again, go back and watch the things from last Monday and Tuesday. I explained that. Basically, the answer is a CPU is kind of made up of multiple pieces, right? There's multiple units, and those units can do various things like multiplying, adding, whatever. And so it depends on the architecture of the CPU. Some CPUs can do multiple things, some can't. Some can do things out of order, some can't, and so on. And so the answer to your question is, like, on the processor we're working on, yes. The processor could do something like issue an add and a multiply that are separate on the same clock cycle, and then get them back later on the same clock cycle, for example, or things like this, right? It can have multiple overlapping things going because it can have multiple units, an adding unit, a multiplying unit, and so on. It can have these multiple units there to do these things as long as the unit of the processor is free that it needs to do the operation, it can issue it. It doesn't matter if some other unit is still working on something. And that's the square root example, right? The square root takes 16 cycles or whatever it is. While those 16 cycles are happening, other things that can use other parts of the CPU can still occur. It doesn't, block it out. Now, that wasn't true of the original microprocessors, like way, way, way back when. They just happened in order. And it was true that you just waited however many cycles it took to do something, that's what you did. But modern microprocessors are much more complicated, and they do a lot more every cycle. So it just doesn't work end to end like that anymore. All right, last question. Sorry for my total ignorance regarding the stream, but what of things can be delegated to GPU instead of CPU? So the answer there is really pretty much anything can be delegated from the CPU to the GPU, but you have to keep some pretty basic things in mind, which is that a GPU's hardware architecture is optimized for doing lots of the exact same operation wide, right? So the things that we're doing on the stream where we converted everything to 4 wide arithmetic, GPUs are like much wider than that. They're like 16 wide or 32 wide or 64 wide or stuff like this. So they're way wider. And they really, really want to be able to do things in ways that exploit large sets of wide operations on small chunks of memory at a time, right? Like they kind of want to maximize these sorts of streaming things where they can like get get a bunch of textures streaming in, do a ton of work on them, stream it out to a chunk of the frame buffer after doing a bunch of ops locally on it or whatever. They really want that look of the workload, right? So you have to have code that looks like that. You can delegate pretty much anything to the GPU that you want. You could put anything you want on there, really. They're pretty general purpose now. But if the workload doesn't look like that, the GPU is actually much slower than the CPU at everything else, right? So random access, single wide stuff, the CPU is way faster than the GPU a lot of times, because GPUs are like oftentimes clock slower, or they've got less cache stuff, or they've got less whatever that that's necessary to make these things go quickly. So an Intel processor is really good at doing single-threaded, single-wide code. It's good at that. And so typically you can't just offload your whole game to the GPU and expect anything good to happen. It's going to be awful, right? And so typically when you look at CPU-GPU breakdown, what you're talking about is when you have these things that really do look like graphical or number crunching workloads. Those are the things you can really move over there. But stuff like game logic and moving things around and executing scripting languages and stuff are harder to make work on the GPU. So typically you don't get a win there, and you're better off just using the CPU cores for that, because you've got 4 CPU cores usually with 2 hyperthreads a core or something in modern day, for example. You've got that to work with, and so that's really the better place for those things to happen. All right, I think I'm gonna go ahead and call it because we are over time. So let's go ahead and close things down here. Where did we leave it here? We left our things running fairly pleasantly. Yes, yes. So cute. Yeah. Well, anyway, it's pretty fun to walk around here now. It's going to be fun to ping back to the game and start playing around with stuff now that we have something that can render very quickly. And it's just it's awesome, right? It's like, it's so nice to take something that was slow and make it fast. It just feels good, and this is just kind of zipping along, and like it's nobody's business. And remember, we could barely even move it before, so that's pretty great. And I'm pretty happy with that. So we've got a little bit more I wanted to kind of cover here when we on the renderer side of things. So tomorrow we'll start maybe taking a look at the memory stuff. And then next week we'll take a look at threading. And so I think we've got a little bit more to do here, but as far as rendering is concerned, this has gone blazingly fast. I didn't expect it to necessarily be such a cakewalk, but it turns out processors are so darn fast that we didn't really have to bust out any kind of craziness. Just kind of converting our stuff to 4 wide actually ran great. Intel, way to go, guys. Seriously, good job. So anyway, hopefully I will see you guys back here tomorrow. Again, I believe tomorrow's Thursday, right? So it's 5 p.m. Pacific Daylight Time tomorrow. Hope to see you all back here for taking a look at the memory stuff and just kind of finishing up some of this optimization stuff that we're doing on the pixel loop before we move on to the multi-threading. So hope to see you back here for that. In the meantime, if you would like your own copy of the source code to play around with at home, you can go ahead and get that on handmadehero.org by pre-ordering the game. It comes with the source code. You can download it every night. After I'm done working, I upload it. If you want to support the video series, we also have a Patreon to subscribe to. We also have a forum site, which you can go to ask questions, and there's the annotated episode guide. There's also ports to Mac and Linux if you're trying to follow along on another platform. Community members have contributed ports. And finally, there's a tweet bot which tweets the schedule, so if you're trying to catch it live, that's the place to go for that. It's always got the latest schedule up there. So thanks, everyone. I hope to see you guys again tomorrow. Until then, have fun programming. Take it easy, everyone.